Hi folks, in this lesson we're going to take a look at some applications to force and velocity. So we're going to have to define some vocabulary here. So let's say, let's start with something simple. Let's say you have this farmer that's applying a force in this direction. Okay, so it'll cause the donkey to move in that direction. All right, now let's say the donkey doesn't want to move in that direction. It might try applying a force in the opposite direction. Well, if they're at a stalemate where the donkey pulls as hard in the other direction as the farmer does, okay, so let's get that force, okay, equal and opposite to the force that's being applied. Well, this is what we call an equilibrium force. So a force that counteracts all the other forces that are acting on the object to create what's called an equilibrium. All right, so for our purposes, an equilibrium will mean that the object is not moving. Of course, those who study physics know that that's not the only scenario in which you can have equilibrium. But essentially, if all the forces acting on an object add up to zero, so we know that when we take a force and add it to its opposite, we get the zero vector. So if the sum of all the forces add up to zero, we get equilibrium. Okay, or what we call a net force of zero. Now let's say there's more than one object, let's say there's more than one force being applied. Okay, so in that case there you might have two forces acting on an object. Okay, so if we add them together, we get what we call the resultant force or the net force. So they say this is the net force once I've added the two forces acting on the object. So now, of course, the equilibrium force will be equal and opposite to that force there. All right, so let's take a look at what we have. The sum of all forces acting on an object is the resultant or net force. Okay, we say that an object is in a state of equilibrium if the net force on the object is zero. In other words, if all the forces added together give you zero, and the equilibrium force is the force required to keep an object in a state of equilibrium. Okay, so as long as this donkey pulls with a force equal and opposite to the sum of all the forces that are being applied to it, then it's going to be in a state of equilibrium, and this force is called the equilibrium force. All right. Now, one of the forces that often acts on an object is the force due to gravity. Okay, so the force of being pulled down towards the earth, but very often that's not the information that's given to you. Often they'll give you the mass of the object, and as long as you're near the surface of the earth, you can calculate that force using the formula 9.8 times the mass. Okay, now 9.8 represents the acceleration due to gravity, so you might recognize that formula. Force is equal to F equals ma. Force is equal to the mass times the acceleration. So as long as you're near the surface of the earth, this is the formula that will give you the force due to gravity. If you're on the moon, it's about 1/6 that acceleration, so it would be 1/6 the amount of force being pulling down. All right. Now, before we go on to the next one, let's take a look at another example of something that's in equilibrium. So one of the questions we'll look at is this idea of a piñata that's being held up by two strings. Okay, so before people start, hitting it with the stick, this object is not moving; it's in a state of equilibrium. Okay, so that means all the forces acting on it are add up to zero. So let's take a look at what forces are acting on it. So we definitely have the force due to gravity that's pulling it down. All right, and then we've got the forces in the direction of the strings, what we call the tension. Okay, so we have a force there, and we have a force there, and all of these three forces are going to add up to zero. All right, but in order to solve a problem like this, what we do is we might start with what I'm going to call a situational diagram. In physics, you probably call this a free body diagram. And I'm going to take these forces and draw a force diagram, meaning I'm going to add up all the forces tip to tail. All right, so let's see what happens. So I know I've got my force due to gravity. And so if I take this force here, add it tip to tail. Now remember that this object is in equilibrium, meaning the net force is equal to zero. So that means this force has to close off the shape to create a triangle, because the net force has to be equal to zero. That means that when I go from the tail of the first to the tip of the second, well, I should be in the exact same place. So when you have an object that's in a state of equilibrium, all the forces add up to zero, and that's going to create a closed shape. So if you have three forces acting on an object, like we have here, it's going to create a triangle. If you had four forces, it would create a quadrilateral, and so on and so forth. All right? So many of the examples that we see here, when something is in equilibrium, you're going to see that there's three forces acting on them, and so it's going to create a triangle. So you can already start to think that if it creates a triangle, we might be able to use trigonometry like we did in the past to solve the problem. All right. Now, just a little thing here, that if three forces are in equilibrium, meaning they form a closed triangle, well, there's no one force that can be bigger than the sum of the other two forces. Okay, and that makes sense. Just look at the triangle. Say you take this longest side of this closed triangle, you realize that there's no way it can be larger than the sum of the other two sides. In fact, think about what the longest it could possibly be. Well, I suppose it would be if you have two forces that are acting in the same direction, and then the third force, remember we're creating equilibrium, would just take you right back. It would just be the exact same length as the sum of the other two sides. All right, but definitely can't be bigger. All right, another thing that sometimes comes into play when we're dealing with forces is sometimes it's useful to take a force and break it up as the sum of two perpendicular forces. Okay, so let's see what we have here. We have this force that's going in this direction. Look what we've done. We've taken this force, which we'll call in the x direction, and if you take this here and move it, you see that it's the horizontal force plus the vertical force gives you the vector representing the total force. Okay, now an example that we'll look at later on is, say somebody's pulling on a sled. So imagine you have a sled here, and obviously somebody's way taller than the sled, so the force they're putting on is going in that direction. But you're only interested in the force that's in the horizontal direction, the force that's going to cause the sled to move along the ground. Okay, so that's one reason why sometimes you might want to break up a force into what we call different components. Okay, now be careful. Sometimes those components aren't always horizontal and vertical. You might want to break up a force in other directions. So for example, if this represents a ramp, something moving along a ramp, you're not interested in a horizontal or a vertical force. You're interested in the force along the ground. All right. So the last thing we'll talk about here is where velocity comes into play. Okay. So say you've got a plane and the pilot sets the plane to travel, say, eastward at a particular speed. Okay. So this would, say, represent the velocity function. Sorry, not the velocity function, but the velocity vector. So the magnitude and the direction, the eastbound direction. And that's what a person on the ground would see, the plane traveling in that direction. But let's say the air is not still. Let's say we've got a wind. Okay. Well, let's say the wind is in the exact same direction as the plane. Well, what's it going to do? It's going to make the plane appear to go faster. Well, the plane will go faster. In terms of the pilot, they're still piloting the plane with that velocity, but the net velocity or resultant velocity is going to occur by adding up the velocity of the plane in still air plus the velocity of the wind. So the person on the ground sees the plane traveling at that resultant velocity. So this is why we call this the ground velocity. So the resultant velocity is often referred to as the ground velocity, what someone on the ground would see the plane moving at. Now, of course, the direction of the plane and the direction of the wind isn't always going to be the same. Okay, so let's say the wind has this direction. Okay, then the resultant velocity, what someone would see on the ground, would be this velocity here. Okay, so the resultant or ground velocity is equal to what we call the air velocity, so the velocity that the pilot gives the plane, plus the wind velocity, and the sum of those two give you the net, or what we call the ground velocity. And if you look at the notes here, we have something very similar if somebody's looking at a boat. moving in the water. Okay, we have the velocity in still water, so that's what the rower is, the velocity the rower is giving it, plus you're going to consider the velocity of the current, and the sum of those two will be the net or resultant velocity, or what we call the ground velocity. All right. So in the next video, we're going to take a look at some examples. We're not going to spend a lot of time working on force and velocity problems, but it's just to show how this concept of vectors can be applied quite nicely to these types of examples. So the next video will go through a few of those examples. That's it for now.